Hello friends, my name is D. Raju. I am working as lecturer in chemistry at Government College Autonomous, Anantapur. So in this video, we will discuss about trans effect and its applications. So we will discuss what is trans effect and what are its applications as part of our video lecture. So initially, if we see what are the learning objectives of this lesson are to know about the concept of trans effect, that means what is trans effect and how it is happening, and what is trans directing series, what about this trans directing series, and what are the factors that affect the trans effect, that means which factors will influence the trans effect, and the theories of trans effect. So how this trans effect can be explained by the two theories called electrostatic polarization theory and pi bonding theory. So what are the applications of trans effect? So how we can apply this trans effect in the substitution reactions of the metal complexes? So if we go to the introduction part of this trans effect is the effect which is observed in substitution reactions of platinum 2 square planar complexes. So we will take platinum 2 square planar complexes and we will do some substitution reaction, and the mechanism of the substitution reactions, the kinetics of these substitution reactions can be explained with the help of trans effect. So if you see the definition, the ability of the groups to direct the entering ligand to occupy the position trans to them is called as trans effect. So the ability of the groups. So what is this ability of the groups? Groups means the ligands which are present in the square planar complex. These groups will have an ability to direct the entering ligand. That means an external ligand which is coming into the complex. So they will direct the entering ligand to occupy the position trans to them is called as trans effect. So they will have the ability to direct the entering ligand to occupy the position trans to them. That ability can be taken as trans effect. And these reactions are the bimolecular displacement reactions. That means they proceed by SN2 mechanism. And so here we will understand the trans effect and its importance with one example here. So we will take a complex, platinum 2 complex. This is a square planar complex of platinum 2. Here 3 chloro groups are around the platinum and one nitro ligand is also there. So what we are going to do? We are going to replace the chloro ligand with ammonia ligand. So one of the chloro ligands present here are going to be replaced by ammonia ligand. Here there are two possibilities, because here two types of chloro ligands are there with respect to nitro group, because nitro group is the only one group and the chloro group which is present opposite to this nitro group is called as trans group, whereas these two chloro groups are cis groups. That means these two chloro groups are adjacent to, they are on the same side of this nitro, so therefore they can be called as cis chloro groups, whereas this chloro group is called as trans chloro group. So whenever we substitute this chloro group with ammonia, there are two possibilities. We can substitute this chloro group or either of these two chloro groups. Let us suppose we are going to substitute this chloro group first. So what happens? So we will get a trans complex, because we are replacing this chloro group and we are putting an ammonia ligand here. So therefore ammonia ligand is here and this is a trans complex. Why? Because ammonia and nitro, both ligands are on the opposite sides, or in this way we can say these two remaining chloro groups are trans to each other. So therefore we are calling it as a trans complex. So we are getting a trans complex if we replace this chloro group. And again there is another possibility, as we have discussed. If one of these two is replaced by ammonia, we are getting a cis complex, because in the resulting complex the two chloro groups are on the same side. Therefore this is a cis complex. So there are two possibilities, getting trans and getting cis complex. But in reality, if we see, only this product is the real product which is going to be formed. whereas this product is not going to be formed, or this product is not formed and only trans product is formed. That means what? So one of the possible products is only happening here, and this happening can be explained with the help of trans effect. So this is the importance of trans effect, and trans effect can explain you why this product is only forming whereas the other product is not forming. So then we will go to the other concept called trans directing series. So this trans directing series is nothing but this is the arrangement of ligands. So we will take various ligands and we will arrange them according to their trans directing ability. That means what? So here in this case we have seen here the chloro group which is present trans to this NO2 is replaced by ammonia molecule. That means this nitro group is having greater trans effect compared to the adjacent chloro groups or the chloro groups. So therefore the chloro group which is present trans to this nitro group is got replaced by the ammonia molecule. So therefore this nitro group is having greater trans effect or greater trans directing character. So depending on the trans directing character, the ligands are arranged in a particular way to give trans directing series, and this is a general order. And if you see this order and if we arrange various ligands according to their trans directing ability, the ligands which are placed in this place, that means ligands like Cn minus, CO, C2H4, NO, and these ligands are called as high-end ligands. High-end ligands means they will have greater trans-directing ability, whereas the ligands like pyridyl, ammonia, OH minus, aqua or water, and these ligands are low-end ligands. That means they will have lesser trans-directing ability. So we are arranging the ligands in the decreasing order of their trans-directing ability, and the resulting series is called as trans-directing series. Here sometimes this order depends on the metal complex and also the incoming ligand in our reaction. So the ligands which are present at high end like CO, Cn minus, NO, these ligands, carbonyl, nitrosyl, cyano, these ligands can form the pi bonds with the metal. That means there is a possibility of formation of pi bond between the metal and these type of ligands. So therefore these ligands are called as pi bonding ligands. So that is one thing. That means the ligands which are having greater trans directing ability, they have the chance to form the pi bond with the metal. Therefore these are called as pi bonding ligands, and these pi bonding ligands occupy the high end of the trans directing series. And some of the ligands, as we have already seen, they cannot form the pi bonds with the metals, but their trans effect or trans directing ability depends on the polarizability. That means how much they can influence the polarity of the metal. So depending on that polarizability, these ligands will have the trans effect. So for the ligands like chloro, bromo, iodo, they cannot form the pi bonds with the metals, but their trans effect depends on the polarizability. So if we take this polarizability factor, as the polarizability of the ligand increases, its trans directing ability increases. So depending on the pi bonding nature, depending on the polarizability of the ligand, the trans effect of a particular ligand depends. So to explain how this trans effect is working, we are having two theories. One is called as electrostatic polarization theory, and this is proposed by Greenberg. So Greenberg is a scientist which gave this theory of trans effect, and this is a thermodynamic approach. That means it depends on the stability. So initially if we take a complex of PTX4 type, so this PTX4 type of complex can be shown here, and the dipoles which are formed because of this metal can be shown here like this. So the positive charge on platinum induces the dipole in X. So as we know, metals are positively charged centers. So therefore, because of this positive charge of this metal, there exists a dipole in each and every ligand X. And if the complex is PTX4 type, that means all the four ligands which are surrounding this platinum are same, then the dipoles of these ligands, opposite ligands, get cancelled with each other. Therefore, the net resultant dipole is zero here. Therefore, there is no trans effect. There is no phenomena called trans effect because all the four ligands are same and all the dipoles which are produced here got cancelled out with each other. That means the opposite ligands will cancel out their dipoles. So therefore the resultant dipole is zero. Therefore these type of complexes are, the trans effect cannot be shown in these type of complexes. Whereas if we take PTX3 or PTLX3 type complexes, here around platinum there are three X ligands are there, one L ligand is there. If we take this type of arrangement around platinum, so here see, this is the platinum, one X, second X, third X, and there is a other different ligand L. So here the cancellation of dipoles of two trans x's but not of L and X. That means the dipoles of this X and the dipoles of this X. So these two dipoles will get cancel each other but not the dipole of L and X because L and X both are different, their sizes are different, therefore their polarizability is different. So L is large here, so we are assuming that L is large here and this L is with greater polarizability, therefore we can say that L is having more polarizability than X. And because of this more polarizability, L induces a dipole within the metal itself. Because of its large size with greater polarizability, in platinum too there is a formation of dipole. So there is a formation of dipole in L as well because of platinum. Because of L, there is a formation of dipole in platinum, and therefore we can say that both platinum 2 and L get polarized or distorted. So this delta plus delta minus shows that they are polarized structures, this L and platinum. And because of this polarization or because of this distortion, the bond which is trans to L, that means the bond which is present between this platinum and X, this will get weakened. This bond becomes a weaker bond or this bond becomes more lengthy bond. That means the bond length increases of this platinum and X. So therefore this bond becomes weaker and the entering ligand or some other ligand which is going to substitute, which is going to do the substitution here will easily replaces this X which is present trans to L. So therefore we can say that the L is having a greater trans effect. Therefore, the incoming ligand is easily replacing this X and occupying the position trans to L. So this, in this way, we can explain the trans effect with respect to the electrostatic polarization theory here. So what is happening here? Initially, there is cancellation of dipoles of these X's which are present opposite to each other, and because of the larger polarizability of L, there is a formation of a dipole in the metal itself, and this L also get polarized because of this platinum, and because of this polarization there is a repulsion between the electron cloud of this platinum and X. So therefore the bond which is present between platinum and X will have a reduced attraction between the platinum and X, and therefore this bond becomes a weaker bond or lengthy bond. So this bond which is present between platinum and X, this is a longer bond or weaker bond, whereas the other bond which is present between platinum and other type of X, this is a shorter bond or stronger bond. So therefore there are two types of bonds are there between the platinum and X, and this bond is a weaker bond, and this is going to be easily replaced by the incoming ligand. And the second theory is the pi bonding theory. So how we have seen the electrostatic polarization theory explained the trans effect of the uh, ligands like chloro-bromo which have the polarizability factor. Whereas this pi bonding theory explains the trans effect of the high end of the series. That means already we have seen what are the pi bonding ligands. So the trans effect of pi bonding ligands can be explained by the pi bonding theory, and this is proposed by Chart and Orgel. And these are the some of the ligands which are present at the high end of the trans effect series. And there is a formation of pi bond between the filled d orbitals of the metal and pi or pi star orbitals of the ligands. So there is a formation of pi bond between the metal and ligand, particularly the d orbitals of the metal and pi orbitals of the pi antibonding orbitals of the ligands will involve in the bonding. So therefore there is a possibility of two types of pi bond formation. One is d pi, another one is d pi p pi. That means, so we can see how these d pi and d pi p pi bonds are differentiated. So there is a formation of pi bond between the metal and ligand. Because of this formation of this pi bond between the metal and the ligand, the bond which is present between the metal platinum and ligand L, it will have more electron density, or it becomes a stronger bond. And because of this stronger nature, the opposite bond which is present between platinum and this X will have a lesser electron density, and this becomes a weaker bond, and this leads to the easy replacement of this X by the entering ligand. So here weakening of platinum X bond, which is trans to L, is taking place, and in this reaction, whenever the entering ligands enters here and reacts with this complex, we can see the formation of a distorted trigonal bipyramidal structure as the intermediate. So there are two types of pi bonding possibility, d pi bonding and d pi p pi bonding. So if we can see here, so this is the platinum, and this is a d orbital of the platinum, which is a filled d orbital. So this is a filled d orbital of the platinum, and this is a vacant p orbital of the ligand. There is a formation between the pi bond between these two orbitals. The filled d orbital of the metal is overlapping with the vacant p orbital of the ligand to give a d pi bonding, and here X is getting left here. And whereas d pi bonding, if we take the d pi bonding, and this is a platinum which is having a filled d orbital, and this is the ligand, and this is the d orbital of the ligand, and this is a vacant d orbital, and both are involving in the process. So both are involving in the bonding to give a d pi bonding. In this way, the pi bonding is possible between the metal and the ligand. So these are the theories which explain about the trans effect of some of the ligands. Now we will go to the application. Now we will discuss about the applications of trans effect. The first application is the synthesis of platinum 2 complexes. Here we will synthesize cis and trans complexes of these PtA2X2 type. So here Pt is the platinum central metal, and A is one type of ligand. A may be ammonia PR3. Ammonia or PR3 means trialkyl phosphine. And X is the halo or nitro or thiocyanate. So these are the two types of ligands. Let us suppose first, if the trans effect of X is greater than A, that means this X is having more trans effect than A. Let us suppose PTX4 complex, and we are going to replace one of the X with A. So therefore what happens? One of the X is getting replaced with A here, and as we know, X is having more trans effect than A. Therefore this X cannot be replaced because the trans effect of X is more than A. Therefore one of these two X's get replaced by the A in the next step. So therefore we will get a cis complex because the two A's are on the same side. Therefore we have got this cis platinum A2X2 type complex as the product. So if we take an example, so we will take a platinum tetrachloro complex which is having red color initially, and we are going to replace one of the chloro group with ammonia ligand here because ammonia is A type and chloro is the X type here. So one of the chloro got replaced with ammonia, and this complex is an orange colored complex. So what happens in the next step? In the next step, if we add 1 mole of ammonia again, one of the chloro which is present cis to this ammonia will get replaced by this ammonia. So therefore we will get a cis complex, and this is a yellow complex. So the formation of this red, orange and yellow, this order indicates the formation of a cis complex here. So in this way we can prepare a cis complex. And again if we take another type. So if we start with PtA4 type of thing, so PtA4 type of complex, so we will replace one of the A with X here, we will get this product, and again we will replace another A with X. So as we know, the trans effect of X is more than A, so therefore this X will direct the incoming ligand to occupy the position trans to it. So therefore the A which is present trans to this X will get replaced. So therefore we got a trans complex as the product here. And if we take the example, so we will take a platinum tetraamine complex here. This is a colorless complex, and one of the ammonia is replaced by Cl. So we have got a yellow complex. So one of the ligand NH3 is replaced by Cl minus, and again one of the Cl minus. So again one of the ammonia molecule got replaced by Cl minus. As we know, Cl will have more trans effect than ammonia. Therefore, this ammonia molecule which is present trans to this chloro will be replaced by the another chloro. So we will get a trans complex. So the formation of this yellow color indicates the yellow to yellow. In the second step, yellow formation. In third step, yellow formation indicates there is a formation of trans dichloro complex here. And the second case is if the trans effect of A is greater than X. Initially we have just now we have discussed that X is more than A. Now we will discuss about if A is more than X. So in the first case we will start with PtA4 type, and we are replacing one of the A with X. And again, as we know, A is having more trans effect than X. Therefore this A which is present trans to this X cannot be replaced. Therefore one of these two A's which are cis to this X will be replaced by another X. So therefore we will get a cis complex here. For example, if we take PR3 4 times, so we are taking PR3 ligand here as A. So we are going to replace it with chloro. So one of the ligand will be replaced here, and again we are replacing with another PR3 with chloro, and we will get a chloro complex as discussed above. So we will get a cis complex here. So if we start with PtX4 again in this one. So A is greater than X, trans effect of A is greater than X, and we are starting with a PtX4 type. So we are replacing with A, and again we are going to replace with A. Therefore, because A is having more trans effect than X, this X which is present trans to this A will be replaced by A. So therefore we are getting a trans complex here. And if we take the example PtCl42 minus, we are going to replace with a PR3 because A resembles PR3 here. So we are getting a substituted product, and again in the second step, so this PR3 is going to replace this chloro which is present trans, because PR3 is having more trans effect than chloro. Therefore this chloro which is present trans to this PR3 will be replaced by another PR3. So therefore we are getting a trans product here. So this is one application. In the second application, what we will do, we will distinguish between the cis and trans isomers of platinum X2 A2 complexes. So which is a cis isomer, which is a trans isomer. This also can be found its application in the trans effect. So initially we have taken a cis complex PtCl2 NH3 twice, two types of ligands, chloro and ammonia, two types of ligands. What we will do, we will add thiourea ligand. So that means thiourea is a ligand which have NH2CS NH2 structure, NH2C double bond S NH2 structure. This is the thiourea, and this thiourea is going to replace the two chloro groups here, because the bond between platinum and the chloro is a weaker bond compared to the bond between platinum and nitrogen. So therefore these two chloro groups initially will be replaced by thiourea group to give this product. And again this complex reacts with 2 moles of thiourea again, because so again we are adding thiourea. That means we are adding thiourea to it. And this thiourea is having more trans effect than ammonia. So therefore these two ammonia molecules which are trans to these two thioureas will be get replaced by again thioureas to give a tetra thiourea substituted product. That means we have started with cis and we have ended with a tetra thiourea substituted platinum complex, because the trans effect of thiourea is greater than ammonia here. So if we take a trans complex, so we have initially we have taken cis, now we will take trans. So we will take a trans complex. What we will do, we will replace one of the chloro with thiourea. Then what happens? So as we know, thiourea is this ligand, and one of the chloro is replaced by thiourea. And what happens in the next step? In the second step, this thiourea is having more trans effect than this chloro. Therefore, this chloro will be substituted by the thiourea, and we will end up with only a di-substituted or dithiourea substituted product. So cis is giving a tetra substitution, trans is giving a di substitution. So therefore, these cis and trans isomers of these type of complexes can be distinguished by the trans effect, and the distinguishing between the cis and trans isomers of these platinum complexes using thiourea is called as Kurnakoff's test. So in this Kurnakoff's test, we can distinguish between the cis and trans isomers, where we can explain the formation of different products with the help of trans effect. So friends, we have discussed what is trans effect, what is trans directing series, what are the theories which explain the trans effect ability of various ligands, and what are the applications of trans effect. And these are some of the references where you will get more information about the trans effect with lot of examples. So thank you very much.